The instrumentation part of MOSFET spectrometer, which consisting of 5 parts. Mainly, the first part is MOSFET drive. Second is the source. Third is the collimator. Fourth, the sample holder, and finally, the fifth one is the detector. So we will study one by one. What's the function of each part? The MOSFET drive. The MOSFET drive, the main function of the MOSFET drive is to adjust the movement of the source towards the sample and away from the sample, which uses the principle of Doppler effect. According to Doppler effect, when the source is moving away from the sample, the energy, the gamma radiations will be decreases, and which is approaches to sample, move towards sample, the gamma radiations increases. In order to match the energy gap of the nuclear transitions in the sample to obtain a proper MOSFET spectra. So the MOSFET drive will move the source sample in relative to the sample in order to adjust the or tune the energy of the gamma radiation, which uses Doppler shift or Doppler effect principle to tune the gamma ray energy to map with the energy gap, so that the proper nuclear transition will affect a proper spectra. We will obtain a proper spectra. So MOSFET drive will move towards and backward. So which is aligned in that way. The second part is the source. Usually in almost all MOSFET spectroscopy in commercially available, they are using iron 57. This iron 57 nuclide is generated from or obtained from cobalt 57 source, which is having a T half of 270 days. Or else, we in some MOSFET spectroscopy they are using T119, T119 also, which is having a uh, T half of 244 days. So here using cobalt 57 as the source, which generate iron 57 very stable and abundant radioisotope, which is a non-radioactive, but its excited state is matched with the principles of MOSFET spectroscopy. We have already covered it in the uh, basic principle part. So here the source is cobalt 57 at a room temperature, which is having a half-life of 270 days, approximately 1 year. And the second is the third factor is collimator. So when a source is moving towards and away from the sample with the support of MOSFET drive, the source emitting gamma radiations. This is gamma rays. This is gamma rays. This gamma rays is widely spread out. So this collimator will bring all the spreaded gamma rays into filter the gamma rays and provide narrow beams, narrow gamma beams, which will be concentrated and which will be narrowing. So this the principle, the function of collimator is to filter the gamma rays emitted by the source and to convert it into narrow gamma beams. Narrow beams. So, and the fourth one is sample holder. You should remember that the sample, there are certain, both the sample and source must be solid phase. Whether it can be crystalline or it can be amorphous solid also, but it neither be non-viscous liquid or gaseous, because in gaseous phase and in viscous liquid recoil energy is very high. Non-viscous liquid recoil energy is very high, so we will not obtain a proper spectra. And the sample and source must be crystalline and amorphous, and the isotopes, there must be high percentage of isotope abundance in the sample, and that isotope must be present in the source also. So both the isotope must be same. Otherwise, there is a difference in the chemical environment that will affect the spectra. So the isotope must be present in the source also, and it should be in abundant. Should be abundant. And how the sample is coated? The sample is coated as a thin layer over the sample holder. It is coated over the or as a thin layer on the sample holder. Okay, so usually we require a larger quantity of sample, but it is non-destructive in nature. That is an important application advantage of MOSFET spectroscopy. We can use the same sample for various analysis also, other analysis also, because the sample is non-destructive in nature. And the second important factor is sample preparation is not a mandatory thing in the case of MOSFET spectroscopy. Sample preparation, because it can detect a very minute, a trace quantity of a very low concentration of nuclei also MOSFET spectrometer can detect. So a separate sample preparation is not required, and we require a large quantity, but it is non-destructive in nature. We can utilize the same sample for other analysis also. So both source and sample holder must be solid. Okay, that's important. Only solid phase is applicable for MOSFET spectrometer. And finally, the detector. The gamma radiations received from the sample holder is collected at the detector. Most commonly used detector is optical detector or Geiger counter. Geiger counter is used to detect gamma radiation, Geiger Muller counter. So Geiger counter is widely used as a detector in instrumentation part. So let me repeat again, which is consisting of 5 parts. The first one is MOSFET drive. The MOSFET drive will adjust the movement of source in relate or in depends on the Doppler shift or Doppler effect to adjust, to tune, in order to tune the energy of the gamma radiation. The source is a cobalt 57 which produce excited excited iron 57 MOSFET nuclei, which is abundant in nature and will provide, which is reliable and provide a proper spectra which we can easily analyze. The T half of the source should be a minimum of 1 year. So in the case of cobalt 57, it is T half is 270 days. So 270 days. Okay. And the third one is collimator. Collimator collect the ender, filter the gamma radiations and to produce narrow beams. This narrow beam strike absorbed by the sample. The sample is kept in the sample holder as a thin layer over the surface of the sample holder. Both the sample and the source must be solid, crystalline or amorphous in nature, not gaseous or non-viscous liquids. And the sample must contain isotope which is abundant, and also the same isotope will be present in the source also, so that we will get a proper spectra. And finally, the detector, which is usually an optical detector or Geiger counter. Okay, and the MOSFET spectroscopy, MOSFET active nucleus, there are mainly 20 MOSFET active elements in the periodic table. Not all periodic elements are MOSFET active. Iron and tin. This is the circled those elements. Iron and tin are widely used elements in MOSFET spectroscopy, and iron, gold, ruthenium, tin, tungsten, iridium, xenon, and antimony, krypton, tellurium, iodine, gadolinium. See the lanthanides. Gadolinium, dysprosium, erbium, ytterbium are the lanthanides, also MOSFET active nucleus. Neptunium is in the actinide series. This is radioactive neptunium, potassium, and cesium. So these are the MOSFET active nucleus. And what are the MOSFET the sources, MOSFET sources, which are not active, but they will provide us the active nucleus. MOSFET active nucleus are provided from or generated from these sources. Cobalt, just like cobalt, manganese also provide give iron 57, molybdenum, palladium, bromine, copper, rhodium, cerium, thallium, Cadmium provide us under cadmium on beta decay provide us this thing rubidium, arsenium, and gallium, etc. These are the MOSFET sources, not active nucleides. That's the difference. These are the active nucleides. So the goal in commercial application of one of the important commercial application of MOSFET spectroscopy is that it can be used to find the purity of the element. So in order to detect the purity of a gold ornament, we are widely using MOSFET spectroscopy in jewelry because it will give exact and the precise value of the purity of the element at its trace level also. That's one of the important application of MOSFET spectroscopy in commercial manner. So this is the instrumentation part. Okay, thank you.